In Java, the specific physical environment where these individual objects are granted physical space to exist is known as the JVM heap. This animated diagram demonstrates the standard object-oriented paradigm. We see a master class blueprint generating 3 independent, identical square shapes. Inside each shape, a distinct data block highlights how every time a class is instantiated, a brand new, isolated segment of memory is carved out. Because these segments are walled off, the variables inside these distinct objects operate completely independent of one another. As you can see, the data blocks within these 3 shapes can change to entirely different values simultaneously. This strict isolation allows complex data modeling to flourish. We can maintain unique, distinct states for every single user or entity interacting with the system, but that exact isolation immediately exposes an architectural limitation. What happens when a piece of data must be universally identical across millions of objects? If every object is forced to maintain its own independent memory space, managing a universal shared state across a massive application becomes a severe liability. Consider a scenario requiring a universal constant, such as an application configuration setting or a global financial metric. If we mechanically store this universal constant as a standard variable within an object blueprint, the JVM simply follows the standard rule of isolated allocation. This animated diagram illustrates the direct consequence. Look at this massive grid of distinct object squares. Creating 10,000 objects under this standard paradigm forces the JVM heap to hold 10,000 identical, redundant copies of the exact same data point. Updating that shared state introduces immediate operational risk. When a change occurs, the system must push a wave through the grid, iterating through and modifying every single isolated object instance individually. This creates tangible processing lag. An efficient system requires a core structural solution, the ability to decouple a shared variable from the lifecycle of individual objects entirely. Java provides a specific syntax solution designed specifically to override the default instantiation behavior. To achieve system efficiency, we must break the rule of object-level allocation and bind the data directly to the structural blueprint itself. That architectural override is the static keyword. Declaring a variable as static intercepts the standard compiler process, telling the system to shift memory allocation completely away from individual objects. This split-screen visualization demonstrates the architecture. On the left, the JVM heap with empty object instances. On the right, class memory, housing a single bright data block, a uni-memory location. As instances generate, they draw routing lines directly to that singular block, bypassing local storage. The JVM enforces a strict single-instance rule. Only one version of this specific variable will ever exist in memory. Mechanically, this variable is loaded into memory the exact moment the class is loaded by the JVM, before any objects are even requested. Contrast this against standard variables, which wait idly inside blueprints until an object instantiation command forces memory to be allocated. This unique lifecycle inherently protects the variable. It cannot be duplicated by new object generation, and it cannot be destroyed during standard object garbage collection. The variable has been elevated from a simple object property to a universal structural constant. The static keyword alters data from a localized property to a centralized truth governed by the class architecture. This clean, typographic layout displays a precise code block, package advanced, and public class state funds. This represents an application managing precise shared states. A package like advanced, housing financial states, requires strict shared governance over specific numerical values. Watch as this visual representation of public class funds expands. Inside, we see the specific interior declaration, static int a equals 100. When the compiler reads the syntax static int a equals 100, it immediately provisions that uni-memory location and assigns the integer value without waiting for further instructions. Normally, initializing 3 funds objects clones the integer, but here 100 remains locked inside the top-level class box, completely separated from the 3 instances below. If one object signals to change 100 to 200, the other instances immediately register the new value via connection pathways. It is crucial to understand that static does not create a freely floating global variable. The data remains strictly encapsulated and governed by the funds class structure. This encapsulation provides the structural integrity required for the advanced package environment to protect shared values from unintended modification. The specific syntax, static int a equals 100, acts as a centralized memory directive, dictating behavior for all future iterations of the class. If a static variable is decoupled from objects, how does an application actually retrieve its data? This generated video demonstrates a single data packet racing along a strict linear conduit, bypassing branching pathways to reach a central node. The source context gives an explicit rule. The data must be accessed directly from the class reference. Physically, a class reference means writing the explicit master blueprint name in the codebase, completely distinct from an object reference. This animated routing map reveals an access anti-pattern. Attempting to route a query through an individual object instance to reach the static variable is crossed out and marked as structurally incorrect. The object route is illogical because the object instance itself does not hold the data in its local memory. The precise syntax implementation requires a direct line. The query connects explicitly to the master blueprint, completely bypassing the instances, executed by typing the class name followed directly by the variable, funds.a. This direct access model completely eliminates the need for objects to even exist in order for the application to read or manipulate the data. The requirement for direct class reference access is the logical, necessary byproduct of allocating shared state completely outside the JVM heap. We have traced the memory journey from the highly redundant default of the JVM heap to the targeted efficiency of class-level allocation. The uni-memory location, the single instance constraint, and the direct class reference are not isolated facts. They form a tightly unified system for memory management. The static keyword decouples system state from object lifecycles. This architecture allows objects to be created, destroyed, or garbage collected by the thousands without ever threatening the integrity of shared, critical data. Packages like advanced and classes like state funds rely on this exact decoupling to execute complex logic without drowning the application in memory bloat. Because static data outlives individual objects, it requires precision. Overusing the keyword can lead to permanent memory consumption that the JVM cannot easily clean up during its standard lifecycle sweeps. The static keyword operates as the mechanism for establishing permanent, universally agreed-upon truths within a dynamic, object-oriented ecosystem.